Hello, welcome back to Math with Patrick and Quill. Today is November 9th, and we're solving problem 313 from the Daily Epsilon calendar. And we should show why the answer today is 9 because that's today's date. We just need to find the integer that is a perfect square and also the product of 4 consecutive odd integers. Got it. So perfect squares are like 1, 4, 9. That's today's date. 16, 25, and so on. They are just produced by squaring our natural numbers. And then when it says that it's a product of 4 consecutive odd integers, consecutive just means in a row. So maybe for an example of consecutive odd integers, we could have, say, 11, 13, 15, 17. And then it does say product, and so we're multiplying these all together. And the idea behind this problem is that we have like an infinite number of options for our 4 consecutive integers to like test out at least, but apparently there is just one solution for today. And my explanation here is that if we're trying to get a perfect square, that means all of our prime factors in our prime factorization need to have an even exponent. Like maybe if we found all the primes here, 11 is prime, 13 is prime, but like 15 is 5 times 3, and then 17 is prime. Once we find all of our prime numbers, and let me write them in order, it'd be 5 times 3 times 11 times 13 times 17. All of these would need to have some kind of even exponent for me to then be able to write it as a square, kind of like this. And so because this particular group of 4 odd integers, consecutive odd integers, did not have any even exponents, this is actually a square-free number. It has no square factors at all, so it's almost the opposite of a perfect square. And one thing to notice here is like if we're trying to figure out, okay, so we only have like 1 5, for example, in all of our prime factors in here, then we could think, well, what would it take to get another 5? Well, we would have to either look at the number 10, which, well, isn't odd, or maybe the number 20, which also still isn't odd. We would have to get to the number 25 or the number 15 to even, 5, to even get the chance of having another 5 in our prime factorization. And again, the goal is to have an even number of them so that we can make a square number. And the distance here is just too great. The distance between 5 and 15 is 10. Between 15 and 25 is also 10. And so we're not going to be able to get more, say, 5s by getting more numbers in here because just our range is too little. So maybe we could try getting, say, a 25 here instead. Like, ooh, there we go. Now we have 2 5s. Let's see what happens here. We would kind of have to get other prime or other odd numbers around it, something like this. And then now we're running into another issue where, okay, we solved our 5s issue, but then we have the same issue with all of the other odd prime factors here. 21 can be split as 3 and 7. 23 itself is prime, and then 27 is 3 cubed. And so now we have 3 times 7 times 23 times 5 squared times a bunch of 3s. And so we almost fixed the issue, actually. We have 3 to the power of 4. We have 5 squared. But then now we only have 1 7 and 1 23. And my claim here is that we're not going to just be able to guess and check this and try to get an answer, because we're always just going to be left over with a straggler 1 or 2 primes. Because the only way for us to get, say, an even number of 7s in our prime factorization is to get a 49 in here, and then the range between the 25 and the 49, again, is too great. And then, furthermore, the range between the 25 and whatever 23 squared is even more great. And so there's really going to be no way for us to be able to get a square number out of this if we have any primes 5 or higher in our prime factorization. So that leads me to believe that we're going to have to dip into negative integers here, because the only way to avoid a factor of 5 is to make sure that the absolute value of our integers is less than that 5. Like I couldn't pick up this 5 or this -5 because that proves to be an issue. Same thing, like I really don't want to pick up any 7s or 11s, etc. So these are our 4 consecutive odd integers, and then if we do find the product of these 4, we do indeed get 9 for today. We get 3 times -3, which is -9, and then finally this -1 brings us back to a positive 9. And that's my explanation for today. Essentially, just investigating what happens if we choose kind of larger consecutive odd integers and noticing that our range here is just too tight, too small for us to be able to get squares on all of our prime factors. Anyhow, I think we're all done. Thanks for watching, and I'll see you tomorrow. Bye.